Okay, so I asked you to do this paper folding activity so that we could start by going over the results. And then this is leading us up into our new family of functions. New unit, new family of functions. That's going to put together some of the stuff that we've done in the past. So if we look at the first investigation, we started with a whole piece of paper. And so I'm looking at the number of folds impacting the number of sections that I get once I fold it. So if I don't fold it at all, I have one whole sheet of paper, one section. If I fold it once, how many sections do I have? 2 sections. If I fold it 2 times, I have 4 sections. So I wanted you to look at this and kind of see if you could see a pattern. Now, in the past, we have looked at table of values. And the first thing that we did to determine if it was linear was look to see if it had what? How do we know if a table of values represents a linear function? Do we remember? Oh, heaven help me. Okay, that's if it's a function. But how do we know it's linear? We investigate the output values, and if we have a constant first finite difference, constant rate of change, it was linear. Right? Y2 minus Y1, Y2 minus Y1. If we looked at our outputs and for our consecutive integer inputs, if I had a constant rate of change, it was linear and I could find the rule, right? I could find the slope, which is that constant rate of change, and then look for the Y value of the Y-intercept and write the equation in Y equal mx plus b form. How did I know if the function was quadratic? I had a constant second finite difference and then constant third finite difference, it was cubic, etc. And you could find the rule. Is this linear? No, if I do the subtraction, I'm definitely not getting a constant finite difference. Is it quadratic? No, in fact, if I were to plot these points, I'd get this nonlinear function graph, right? If I graph these table of values, but it wouldn't be quadratic. In fact, if I continue to investigate the pattern, were you able to get the equation y equal 2 to the x? And if so, where did that come from? Could anybody get that formula? Nobody was able to get it? Nobody.
Because every time the x value increases by, or the y value increases by 1, then the x value is doubled.
It's doubled. I like it. So if I were to look at y2 divided by y1, what would I get? I'd get a constant ratio, right? I'm multiplying each time. So if I were to work backwards from our further y2 to y1, for example, 64 divided by 32, that equals 32 divided by 16, which equals 16, so on and so on. So my constant ratio is what you should recognize for this family of functions known as an exponential function. So our new family of functions that we're working with are exponential functions. They have a constant ratio. In this particular case, the constant ratio is what? 2. So that's where this base comes from. That's where the base comes from. So for an exponential function, we have y equals some constant ratio raised to the x power. The unknown value x is the exponent, hence the name exponential function. Now, one other thing I want you to pay attention to as a little foreshadowing is look what happens when our input is 0. So when x is 0, my output is 1. Well, that's true for any number other than 0 raised to the 0 power, right? So that makes sense where we would get the 1. Where that appears in the formula, we're going to talk about it a little bit later. So how would this be different if I used an 8.5 by 11 piece of wax paper instead of regular paper? Well, I'd still get the same results, same number of sections, same equation to represent this function, but it may be harder to fold the thicker paper. Has anybody seen the Mythbusters where they do it with the giant football field full of Yeah, you seen that? That's pretty cool. Answers the question. What's the maximum number of folds you can get? Now, if we continued with the investigation and did part 2, we're using the same process, but the difference is instead of looking at the number of sections, we're looking at the area of the smallest section. So with no folds, I have the whole piece of paper, one section. If I fold it once, I have 2 sections, right? But what is the area? Well, it's half of the whole piece of paper. If I fold it again, then what's the smallest section? It's 1/4 of the area of the whole paper. So if you investigate this table, again, it's not linear. There's no constant first finite difference. There's no constant second finite difference, etc. However, you should be able to recognize that there is a constant ratio. And what is the constant ratio in this case? If I do the division, 1/2. Beautiful. So guess what? That is my base. So do you see that? Now, how is that represented in the graph? Well, when we had a base of 2, it rose left to right. So that's exponential growth, increasing. If this was a fraction in this case, a proper fraction, we notice that it was falling left to right, which we will see is exponential decay. Now, what we're going to do in class now, ever so quickly, because after we do this investigation, we are going to do the formal notes. So we do have quite a bit to do. But let's go ahead and ever so quickly do this investigation and collect some data and then do an exponential regression on the calculator. Exponential regression. So what you're going to do in pairs, and those of you who are online, I'm going to turn my computer around so you can follow along with one of the pairs in here and get their data as they do it. So every pair is going to get one of these. You're going to have, I've disinfected them. I mean, there's little wipes in here. They've lived in there all night. So one person is going to be in charge of, preferably, you know, to keep sanitary. One person will manipulate these. The other person's going to record the data. Or if one person wants to manipulate them and the other one does the removing, you know, that way you're not touching the same thing. Okay. So how do we do this? Well, you're going to start with one box per pair. You're going to take them, and you may want to do it on the floor so we can space out and they don't fall off the desks, etc. So you're going to take it, you're going to shake it, you're going to dump them out. They're 2 colors. One side is yellow, the other side is red. You are going to remove the yellows. So for trial number 0, that's how many you're starting with. Everybody has a different number. Starting with the number that we have in here. Dump them out, remove the yellows. So one person can remove the yellows. They are out of the game completely. You're going to count the number of reds left. That's your first trial. Then, that's number 1, not 0. 0 is what you start with, initial. 1 is removing the first set of yellow. From those red ones that remain, put them back in the box, shake it, dump it out again. One person can be removing the yellows again. You count the number of reds left. That's your second trial. Do it again until you get down to about 5. After 5, the data is not going to help us anymore. Okay? After you've collected the data, I would like you to get the wipes. And I would like to wipe on the bottom, wipe on the top, and give it back to me. I'll shake it around so we can decontaminate them for later. Okay? Do we understand what we're doing? Once you collect the data, I want you to investigate it. Make a scatter plot, put it in the calculator, do an exponential regression because maybe that constant ratio isn't as obvious to find. So this is real data, right? So find me the equation and then continue on to this next page and let's see if we can interpret it. Then we'll do the formal notes. It should take you no more than 5 minutes to collect the data and then maybe 5 minutes to answer these questions. Okay, so one person in a pair, come get these. Quickly, quickly, quickly. We have lots to do. Lots to do today. Who wants? Come. Come get them. Quickly, quickly, quickly. 5 minutes to collect the data, 5 minutes to answer the questions. Social distance and be sanitary. Why don't you come do it here, and then as you do the experiment, can you please tell them your data?
Yeah.
Okay, so what you started, well, don't get too close, right? Can you be in charge of?
I will.
Okay, so they're going to tell you the data as they collect it. And then you're also going to tell me your data, so I can put it up here. Try mine. Well, actually, I don't have to do that if you're telling me. Yes. Count all of them to begin. Dump them out, right? And then separate them so that you have yellows and reds, right? But count all of them because that's 0. Okay. Remove the yellow and that's the red. Okay, count the reds. Okay. And let's do this efficiently because we have notes to do. I want you to come back to the tutorial and finish the notes.
All right. Oh, 100. Yeah. So for the first one, it's 100. Like starting off with 100 base thing.
Count the reds. Or yeah, do the red right here.
You put it all back and shake it and then you do it.
No, you move the yellow. Just the first one. And then we put it back in and shake it.
Oh,
Oh, no. You gotta put them inside.
Counting the red. I know.
So now we take all these So put the yellows back in the box, shake it again. No, I'm sorry, put the red back in the box. Right, because the yellows are out of place. So just
Oh, I
push
didn't
it
see the
aside.
yellows over there. That was very unlucky.
Okay.
True. I didn't
So
see the
that's
yellows over
0,
there.
right?
Yeah, you got because you're closer. You have to keep them updated.
Okay, the first number is 100 and the second one is 43.
I didn't see the yellows.
Make sure they got it.
I already had it. Only one hour.
Did y'all get that online? The initial 0 for trial number 0, we had 100. And then trial number 1, after they removed the first set of yellows, was 43. No, okay, everybody, well, they potentially have different starting numbers. Starting? No. All of them is what? And then that was your first iteration, so now you have to count the ones that you removed, so you have 0. Right, 0 is when you split all of them, okay?
What other one?
Which is fine, okay?
Do you want to just do that last? How many there are?
Well, if you've already removed the yellow, you can just count the yellow. Okay, right? Yeah.
That's good.
What are you doing?
Okay, I guess
Okay, then we have what? 18.
After 18 is, I'm sorry, after 43 is 18. 18. So let me go, I'm actually gonna write yours here. So we said the first one was 100, or the second one was 43.
yes, and then 18.
So
Do we do it until there's less than 5?
Well, total about 5. 6? Or you stop.
Okay.
You just write that number as your last one. Now, we need a wipe. Put a wipe at the bottom, put all of them in, and then put a
11.
wipe on top.
11.
Hold on, put it back.
Wipe at the bottom, put them all in, and then wipe at the top. And then let's go ahead and do an exponential regression, please. On the calculator, you should, oh,
And that was not even built, man. How it was 6. And now we're done.
oh, okay. We
Because
need
it's like less than 5. And then 6.
wipe at the bottom,
Alright.
and then a wipe at the top. Stand here. Okay, let's do an exponential regression. Okay, then what do we have after 11 and 3? Okay, for this group in front of me, this is their data. Every group is going to have different data. Different data. Here. There's wipes all over this place. There's wipes everywhere. Thank you. Exponential regression. We're getting our calculators out and we're computing an exponential regression. Do we remember how to do that? Do I need to walk you through the steps? Does anybody need to see the steps on the TI?
Yes.
Yes, okay, I can do that. So you're entering in your X and your Y values into lists, and then you're calculating an exponential regression. It is going to give you the equation, and we're going to talk about that, but I'll walk you through the steps on how to find the regression. No, it's all right.
Thank you.
Thank you. Okay, let's talk about how to get back to where we enter the list. Does anybody remember how we enter in lists? You need to be able to do this. How do we enter in lists? We go to second. Oops, I hit the wrong button. Second stat. Oh no, that's not where I enter them in. Just stat. Hit stat, right? And we're going to edit our lists. So you're putting your data in there. So everybody's got different data, right? This is just data I have from yesterday. You are putting in your lists. Once you enter in your lists, we're going to talk about how to perform the regression. So stat, enter in your lists, be ever so careful. We can create scatter plots by graphing and making sure our plot is on. But let's talk about how to do a regression. So once you've entered the list in, what are the keystrokes to be able to actually get the regression? Where do I go? Bless you. I hit stat again, but now I'm not editing my list, I'm calculating. Now what am I calculating? Not a linear, not a quadratic or cubic or any of these. Oh, look at this one, exponential regression. So select that. Now make sure that you are performing the regression on the correct lists in the correct order. Can we store the regression equation? How? Vars. Y vars, because it's a function. Hit function, there it is. I'm going to put it in the first one. And then it's going to calculate the exponential equation that best fits this data. So what is it giving you? It is giving you y equals a times b to the x. So what I want you to do, this is mine, this is my data. Look at that and see if you can interpret what this means with respect to your data. Answer the questions on the next page and let's go over them. So take a...
Wait, sorry.
Mhm.
I'm so
That's okay. What are we confused by?
okay. I got the Y-bar.
Answer the questions. The rest of y'all answer the questions. Yes, ma'am. Then hit enter.
Okay. And then I have like a whole list of like Y1, Y2.
Okay, select Y1 because we're just going to put it in the first equation. So I can go to Y1 and there it is.
Mine does not look like that.
Well, you have to enter it in and have it create the equation first. And then you can go back to Y and see that it's there. So I went to stat, calc, I went to exponential regression, and then I stored it by doing my vars, y vars, function, y1, and then I calculated it and it gave me this information. That is your equation, y equals a times b to the x. That is your exponential equation.
Why don't I have an all?
Your diagnostics are not turned on for that. Don't worry about that because that's irrelevant with respect to exponential functions. We only looked at that when we were working with a different type of function, a linear function. Right? Okay, and I could graph it and I could look at tables of values, but you know, I see that and I should expect to see a graph that looks like this. And we're answering the questions, and then we will go over the answers and then do the notes. So we're answering the questions, and then we are going to go over those answers and then move on with the notes. Can you all give me your equation that you got?
1 and 2, open parentheses, 1, 4, close parentheses.
And how many did you start with?
Started with
100.
First rows.
Okay. Somebody else, can you give me your equation? Anybody? And how many did you start with? Anybody else? Another equation? Anybody else have an equation? And how many did you start with? William, you want to give me your equation? Point what?
0.5.
Mm-hmm. And how many did you start with? So I'm kind of prompting you here. So to answer these questions, now recall the equation that we are working with respect to the exponential function is this. Y equals a times b to the x. That's what the calculator gave us when we performed the exponential regression. My question is to you is looking at these components, the a and the b value, perhaps do we understand what they represent with respect to our problem? So what does the equation give you for starters if I let x equal 0? If I let x equal 0 in any one of your equations or any exponential function written in this form, if the x value is 0, what are you going to end up with? What is your value of y going to be? It's going to be a, right? And what does that a, if I let this equal 0, this becomes 1, right? Anything other than 0 raised to the 0 power is 1. 1 times this value here is what your output is if your input is 0. So on the graph, what does that represent? The y value of the y-intercept. Exactly. Now, how does that relate to the number of color counters you had?
It's the starting.
It's an approximation of the starting population, the original number you started with. So that's kind of why I was asking for this, because if you look at that, I mean, this is real data. It's finding the exponential equation of best fit for your data. Now, so that's the answer to this one, right? So that's the y value of the y-intercept when x is equal to 0. And A represents your starting value, what you started with. Now, if I were to look more particularly at B, what does the value of B represent in your exponential model?
The difference.
Okay, but not difference.
Yeah, not different.
What did we call that?
Be like, first time.
What'd you say, Olivia? I can't hear you. It's the constant ratio, right? And what does that represent? That represents, right, how we're decreasing our values at each iteration, right? That was the probability that the counter would land on red showing, right? So we're decreasing the number that we have by a half each time. And that makes sense, right? Isn't that interesting though? No matter what we did, we all got about a half. That's beautiful that you're relating it to probability. Yes. Yes, you are absolutely correct. So how does this compare? Well, with the paper folding, it was exact. We could calculate that constant ratio. However, with this is real data that we're collecting. Now, can anybody think of an example maybe that's very relevant to our world, especially from starting last year, of where we might see a model like this? Well, last year, when we were first learning of the coronavirus, right, they were looking at the increase in positive cases. At the start, when we were looking at that, guess what? It looked exponential, right? It was increasing. And if you remember, everybody kept talking about, well, when is it going to peak and come back down, right? So at the start, they were saying, oh gosh, this is exponential. But if it had continued on an exponential, well, then it would affect infinitely many people and we'd all die, right? It would be over. So we had to bring it back down, right? So then it was no longer an exponential model. It turns into something else, and we'll talk about that. But at the start, it was resembling exponential growth. And they were talking about a growth rate in the news. So what I would like to do next, any questions on that? Was that fun, that cute little experiment? I thought it was nice. Let's go to the notes. We are going to the notes. And let's formally discuss exponential functions. Exponential functions. So we saw the parent exponential function. There's the general form right there. Now, A can't be 0, because if A is 0, what am I looking at? Well, if A is 0, then I have y equals 0. What kind of function is that? More importantly, constant. Yeah, it's a constant function. So it's the value of B that we're most concerned about to tell us the nature of this function. So this B value here is the base. It's the base that we are raising the unknown x to, the x, that our input. So it is that B that tells us a lot about the nature of the function. X, well, that's just your exponent, right? Now, depending on that value of B, I may have exponential growth. When do I have exponential growth? I have exponential growth when that B value is greater than 1. I have what is known as exponential decay if that b value is a proper fraction, so a number between 0 and 1, a proper fraction. So if I have growth, I am rising left to right. I'm strictly increasing. If I have a b value that is a fraction, I am falling. I am decreasing left to right and strictly decreasing. And we've talked about where functions are increasing, decreasing, and constant. Now, what I should point out to you, and it should be kind of obvious, is that no matter how far I decrease, let's say I have exponential decay, no matter how far, I'm going to keep dividing by half, by half, by half, by half, by half, by half, multiplying by half, by half, by half. Am I ever going to get to 0? No, I'll never get to 0. So guess what? We have a horizontal asymptote at y equals 0, and that is true for our parent, right? If I shift this, if I translate it, if I vertical shift it up or down, that horizontal asymptote moves with it. So we can easily identify that in the equation. So let's take a look at this parent function. So I have a parent function, y equal 2 to the x. Well, I could easily substitute in values for x, get the output values. Let me ask you, is there any restriction on the domain values for this exponential function? Are there? Can x be anything, or do I have any restrictions on my x values, my input values? Yeah, it's all real numbers. X can be anything. So negative infinity to infinity. So it doesn't matter which ones you choose, but you know, we like to see the y-intercept. So what is the y-intercept? When x is 0, y is 1. And then I could continue, right? And I know that my constant ratio is 2. Right? So if I divide. So I know this, and I can also say that, well, what's my a value in this? In my equation, y equals a times b to the x. I said my constant ratio is 2, but what is a? Well, how'd you get that?
It's the y.
That's right. So y value of y-intercept. So that's 1. There's technically a 1 here, but I don't need to see it, right? And that's true. There's a beautiful little exploration if you want to play with that on Desmos in your packet, changing those values of b, making them larger, making them smaller, etc. What's happening and how that's impacting how quickly we go to infinity. Now, what is the range for this parent exponential function? The range. That's right. It's not including 0 because we have a horizontal asymptote at y equals 0. Beautiful. So the x-axis is a horizontal asymptote. Okay. So let's look at a few examples. Let's say I give you some exponential functions and I ask you, is it strictly increasing? Is that exponential growth, meaning b is greater than 1? Or is it strictly decreasing, meaning I have exponential decay, meaning b is a proper fraction, a value between 0 and 1? Or is it neither? Is it even an exponential function? First one, is it growth or decay? Is it strictly increasing or decreasing? It is increasing. B equals 2, so b is greater than 1, so it is growth. Okay, what about the next one? It is decay. So b is a half, so b is a number between 0 and 1, so it is decay, so it's strictly decreasing. Now, let's talk about graphing exponential functions. Again, you should be able to look at each of these and tell me, is it growth, is it decay? So is A growth or decay? It is decay because B is 3/4. Now, if I wanted to, so I know it's going to fall, right? Decrease left to right. So if I wanted to graph this, what would I want to maybe include? What other value do I know from this? The y-intercept. So from here, I know that my y-intercept is where? 0, 10. So y-intercept is 0, 10. Thank you for giving it to me as a point. So I know it's going to look like this. And I know that I have a horizontal asymptote, right, at y equals 0. Because there's no plus or minus after this, vertically shifting it. Okay, if I wanted to do a quick sketch of the next one, is it growth or decay? It is growth, and how do you know that? B is 1.05. Yeah, it's greater than 1. And do I know the y-intercept for this one? 0, 1. So I could do a quick little sketch of this one as well, knowing that I pass at 1. And this, oh, this is growth, so it's going to look like that. And again, horizontal asymptote at y equals 0. We could subsequently state the domain and range. Domain is all real numbers. The range would change depending on whether that horizontal asymptote moves, whether there's a vertical shift. Looking at the next one, is it growth or decay? And we know that because B is 1.2 greater than 1. Do I know the y-intercept? 0, 5. So I could do a quick sketch here. Again, it's growth. This is 5. So I know it's going to look like that. And again, horizontal asymptote at y equals 0. Now, if I give you the next exponential function, so I've given you this exponential function, is it growth or decay? It is decay because B is less than 1. So it is decay. And my y-intercept is what? Be careful. When x is 0, what is y? When x is 0, y is, what do you say? That is correct. Do you see y? Be careful, right? Because what transformation have I performed? A vertical shift down, right? Because of this, I now see that I've shifted down. So where's my horizontal asymptote? Good. Now, put this in your calculator. I didn't need the calculator for this one, but go ahead and put this function in your calculator into y equal, being ever so careful to put it in your calculator. Use the little caret, right, to show the exponent of x, and find me the other two values. Does anybody need me to do this and show you? Are we okay? Where am I going on the calculator to find these values? Once I enter in the equation. More particularly, because you're not entering in lists, right? You're entering in the equation. Did we find the values? Where did you find them? Oh, okay. Well, what if we wanted to graph that function and then tell me the values? What could we do? You could go to the table, right? You could go to the table and find when the input is -5. When the input is -5, what is the output? Okay, and for x equal 5, what did we get for the output? Did we get those? Does anybody have trouble getting those values? You what? Say that? What is it, Olivia?
Where do you want to center those?
Well, I would go to y equals and I would enter in the equation. So I can show that to you. Okay, so if I go to y equals, let me clear this. I would put in 13.49 times, and then 0.967 caret. Where's the caret? Do you know where the caret is?
Yeah,
Where do you see it?
on the right under clear.
There you go. And then you'd enter in x. Okay, so there, oh, something happened to my equation here. Where did my, let me insert, sorry. Something happened with my little, let me insert 13.49. Okay, so I could graph that. Now I may have to adjust my window, right?
You forgot -1.
Okay, I'm sorry.
Did you put in the -1?
Oh, did I forget the -1? Oh, thank you. The problem is it doesn't let me type on my keyboard. I have to do it here. My apologies. Thank you for catching that. So there it is, because that's on my vertical shift down. And then if I wanted to find the output for when the input is, oh, look at there, I just went to the table. So when x is -5, I got 14.954. And then this we knew, right? And then this we found. We good? Okay. Now, if you go to the next page in your notes, the next page in your notes asks you to graph. So let's talk about the transformations that we would see if we were to graph. So let me go to Desmos. And let's talk about the transformations that we should see. And y'all should be able to recognize these immediately. So our original function, so the next page on the notes tells us what function. Give me the equation. Y'all. 2 to the x. So there's my parent. Oh, okay. So there we go. Very good. So in that function, what is your underlying parent function? So you've been given a function that has been transformed, and hopefully you recognize the transformations. But what is the underlying parent function? Y equal 2 to the x, right? If I strip away any transformations, this is my underlying parent function. But I have performed a transformation. So instead of having a y-intercept of 0, 1, what have I done to this parent? Well, I have subtracted 2 from this equation in the notes. So how is that reflected as a transformation? It is a vertical shift down. So I could actually put both of them. There's the parent, and then I could take this, and then I can shift it down too. There we go. Ah! So where's the horizontal asymptote there? Y equals -2, right? So the domain is all real numbers. The range is open parentheses -2 to infinity, and then we have the horizontal asymptote at y equal -2. Looking at the next one, the next example in your notes, what is the underlying parent function? Again, it is y equal 2 to the x, but I see how many transformations? 2. Okay, so the first one is to this x value. So if I subtract 5 from that x value, what do we expect the transform function to look like, the image function? By subtracting 5, what am I doing to this parent? I'm horizontally shifting which direction? To the right. Oops, let me go back up here. To the 5, oh heavens. Let me put this in parentheses. I'm shifting it to the right, just like we would expect. Because when we impact the x values, right? Remember, we're doing the opposite direction. Now, so that is a horizontal shift to the right 5 units. Is that impacting my horizontal asymptote or my domain? No. Is it impacting my y-intercept? Yes, it is. Is it impacting my range? Right now, is this impacting my range? No, my horizontal asymptote doesn't change, my range doesn't change. It's 0 to infinity. However, in the notes, it tells me to do what other transformation? That's right. So by adding 4 to the entire input here, right? I'm adding a 4, so I'm impacting my output. So that plus 4 is a vertical shift up 4. So does that impact my domain? No. Does it impact my y-intercept? Yes. Does it impact my horizontal asymptote? What is my horizontal asymptote? Y equals 4. So do you see how that vertical shift is going to impact my horizontal asymptote? So you should be able to graph these. You could always take a table of values, or you could look at the stripped down parent function and then perform the transformations. It's up to you how you want to do it. Okay, now the next thing that I want to talk about is E. Okay, so we know pi. We know I is the unit imaginary number. What is E? It's another very fancy number that we have to be familiar with. So let's go back to our calculator and let's talk about E. So calculator knows E. So if I go to my calculator, can you find the button E? In particular, what if I look at y equal e to the x, where the base is e? Do you see that function on the calculator? I'll give you a hint. There it is. Right? So I could hit, you see this little blue? So I'm going to go to second E, and I can raise e to any power. So if I want to know what the value of e is, what would I put in as the power? 1. So what is e? There it is. So e is a very special number. It's known as the natural base. It's an irrational number. It is obtained using the formula that is written in your notes, that 1 plus 1 over n, all to the nth power. So as we're increasing n, we're getting more and more decimal approximations of this value e. A Swiss mathematician Leonhard Euler came up with this beautiful number that you will see a lot. So let's appreciate it. Now, if I enter into the calculator y equals e to the x. So now let me get rid of this, and I'm going to put y equal e to the x. Okay, there's a function. Now, is that growth or decay? Growth, because e is a number a little greater than 2, right? 2.718, so on. So if I were to graph that, I should see growth, exponential growth, and there it is. Can you tell me the different values of e to the x when x is -5, 0, and 1? If x is 1, what is the output for y equal e to the x? You should know that off the top of your head. Now, to figure that out, we could also go back to the table and look at that. But for x equals 0, you shouldn't need that. So let's go back to our notes and see where we are. Share my screen. Okay, so we're looking at e. So when x is 0, what is e to the x? 1, because e is just 2.7, right? Raised to the 0 power, 1. They got cut off. What is f to the -5? Excellent. And f of, not to the 5, f of 5, f of -5 and f of 5. Yeah. Okay. Now, where do I see this? Where do I see these exponential functions? Well, we talked about how it's one way used in population growth and decay. Another place where you're going to see the applications and the use of exponential functions is money. So you want to invest money, you get a certain amount of interest compounded, and hopefully your money grows, right? Or if you take out a loan at a certain rate, you start paying, it's going to decay. So we need to be able to understand how we can use exponential functions in money applications. So let's say we are looking at the application of compounding interest. Compounding interest. This is the formula for discretely compounding interest. What does that mean? That means I'm going to invest an amount of money, and ever so often, it's going to apply interest. It's going to add interest. And it's going to add interest for a certain number of times a year. So when you go to the bank, you can choose different accounts that give you different interest rates that is compounded at different number of times of the year. So let's look at the components of this beautiful exponential function. So P, this little P, is your principal. It's the initial amount. Principal is the initial amount. So you may go to the bank and you may invest some money. That's the money you're investing. Guess what R is? Can we guess? The annual percentage rate. Yes, you are correct. The abbreviation that you may have seen before is APR. That's your annual percentage rate. N, this little N, is telling you the number of compoundings per year, how often we're accruing interest. So in the word problem, if it says it's compounding annually, what is N going to equal? Semi-annually. 2. Quarterly. Monthly. Daily. Yes. And what do you think T is? The time. That's exactly right. The number of years that you're investing. Number of years of investment. Okay, time that you're investing. And that output A, the output A is the amount that you end up with. So that's the accumulated value of the interest. After a certain number of years of investment, compounding a certain number of times per year at a certain rate. So if I'm looking at annual, so for annually, if it's compounded annually, let's look at that formula and what it would be. It would be P times 1 plus R, N is 1, to the T. So that's for annual. So let's look at an example. So this one has to do with population. Let's see if we can read it and interpret the different pieces of information and how that applies to our formula. So our formula that we're working with is A of T equals P times 1 plus R to the T. A city population which was initially 15,500. What is that value? That is P. Has been dropping. Oh, dropping 3% a year. So what is that impacting in the formula? That is impacting R, but since it's dropping, we know we're subtracting, right? The population is decreasing at a rate of 3%, so 0.03. So that's our R. So I can continue. I kind of already knew that it was going to be annually, so I omitted the N, but we would take into consider N mainly with money. Ooh, we said it was dropping, so we have to subtract 0.03, and then that's T. So there's my exponential function that represents this information. Now, you are using a graph or the equation to predict, so we're doing predictions from this equation when the population will drop below 8,000. So we're solving for what variable? If I want to predict when, we're trying to find t. And so what am I looking for? I'm looking for when the population is 8,000. So where is that represented? Yes. So I want to know when the population will be below. So when this is below 8,000. So it'd be nice to know when it is 8,000 because any time after that, it will be below it. So can we put this into the calculator and answer that question? Now you can do this using a graph, right? So I could put y equal 15,500 times 1 minus 0.03 to the t, and I'm going to get growth or decay. I'm going to get decay, right? So I know it's looking like that. So it's starting at 15,500 and I'm decaying. So I want to know when it gets below 8,000. Right? So couldn't I graph that, and couldn't I graph the line y equal 8,000 and look at where those two graphs intersect to tell you at what time t? Because my input is t, my output is A, the population. A of t. I could do that, but there's also another way I could get the answer. What's another way I could get the answer? I could put this equation into the calculator and I look at my table for when my output is less than 8,000 and see what my input is. Can you tell me the answer to this question? When will the population be below 8,000? (2.2) 22. Between 20 and 20, oops, 20 to 21 years, right? Do we get that answer? Okay, can you then now answer the next question? What will the population be in 3,000 years? So what am I using that 300 years to be? T.
Can you show how you found
How I found what?
the 20 to 21?
Yes. Give me 1 second. So that's what we're finding here. Okay. So you put this equation in the calculator, Olivia. We're running out of time and I got to do the next example. So can I walk you through the keystrokes a little bit later?
Yeah.
You're putting this equation in the calculator. You could then put this equation into the calculator and then you calc the intersection. That intersection is going to be at 20 when the input is 20. Or you could put this in the calculator and look at the table of values and find when the output is 8,000. That will be when t equals 22. What do we get for this one? 800. 8,000. So what did we get for the answer? What will the population be? The population in 300 years will be what according to this model? Can anybody answer? Anybody? Yeah, so approximately one person. Right? Based on this model, we can't have half a person, right? So we're rounding down. Approximately one person. Now, this was the formula we said we used for population and interest that was compounding a discrete number of times per year. What happens if I'm compounding continuously? Meaning not 1 or 2 or 3. I mean like continuously, like it's always compounding. There is something called the Pert Formula, and we use this, and this is where we incorporate the number E for compounding continuously. So if I'm given this example, and I said when Mary was born, she deposited $10,000, what is that going to represent in the equation? Oops, that's our initial deposit. Yes, that's our P. Okay, so I'm substituting into this formula 10,000 for P times E. What's the rate? 7%. So that's R. And then we want to know how much she's going to have after 18 years. So I'm substituting in 18 for T. If I substitute in 18 for T, how much money does Mary have? You tell me. How much money? Yes. Yes. You should be able to get that as your answer. Now, you have my math lab. I would like you to do this next problem, but I want to tell you what you have for homework. You have my math lab, and you have a worksheet. The worksheet has already been posted online. Okay? So what you are doing on this worksheet, it walks you through the steps. We've already talked about it. You are looking at these table of values. Okay, you have tables of values. Oh, you can't see that. Let me share this. Oh, I can't stop that. Well, here, this is it. Table of values. You are to determine if this table of values represents a linear function, a quadratic function, or an exponential function, or neither, none of those. If it's linear, you see that first finite difference that's constant, that's your slope. Look for the y value of the y-intercept, write the rule. If it's quadratic, you will see that second finite difference. And what does that represent in terms of the formula? Do we remember? No, we don't. 2a. Remember that? We can find A, we can find C, the y value of the y-intercept, write the rule. If it's exponential, what should we see? That constant ratio. That's your base. We look for the y-intercept. That tells you your A, right? Write the rule. Or it's none of these. So your homework is the My Math Lab and this. And then if you want to explore the different bases, you can. There's a little exploration in there. There's also practice for graphing in the packet. So if you want to, practice your graphing, we are moving on Tuesday when I see you, Wednesday, whenever I see you next, Wednesday. We are moving on to the next family of functions that uses exponential functions and that line y equal x to get its inverse. So we're putting it all together. So go ahead and try this problem here, and let's see if we can come up with the answer, and then you are welcome to work on the table of values or My Math Lab. This next one's interesting. It's like when you go to the bank and you try to figure out where to put your money. You want to get the best deal, you do the math. Yes. A paper clip.
Or
Nothing that big. No, okay. I don't. I'm sorry. I don't. Olivia, did we want to go over anything, any keystrokes, or were you able to get the calculator problem?
I just don't understand what to put into my calculator.
I'm sorry. Can you stop shuffling papers and ask me the question again?
I just don't understand what to put into my calculator.
Okay, so let's go back to the calculator. Okay, and I'm entering in the equation. Let's see what the equation was.
Can we do the example 4?
Yeah, that's what I'm trying to go back and see. Okay, so I'm going into the calculator and I'm going to put in 15,500. I'm putting in the equation that we are given. Parentheses 1 minus 0.03 close parentheses raised to the x. Do you have this equation in your calculator?
Yes.
Okay, then I'm going to graph it. Now, why don't I see anything? My window, right? My highest y value is only 20, but I know my y-intercept is 0, 15,500. So maybe I need to change my window. Oh, shoot. Sorry, hang on. Let me go back to my window. I have to do it on here. So let me clear this and let me put -2 because I don't really care about my. And then I'm going to go to 100 just for kicks. And then I'm going to scale it. My y min, I don't need to see anything negative because that's population. And then I'm going to go to 20,000 because I need to be able to see the y-intercept because it makes me happy. Okay, there's my graph. Now, I'm trying to figure out for when the population will be below 8,000. So if I go to my table, I'm below 8,000. Oh my gosh. Well, the population's 18,000. Okay, when does it go below 8,000? After 21 years. Do we see that? The input is years, the output is the population. So I can answer that question this way. If I wanted to know the exact value, I could go back here and I could also graph y equals 8,000. Because if I graph that, I'm going to see exactly at what point I go below 8,000. So how do I calculate that? I can go to second trace and I can look for the point of intersection. And I can go first curve, second curve, and then it's going to tell me exactly when that happens. Do you see that?
Can you go back to your y equals?
Mm-hmm. Mm-hmm.
So wait, you just put in 8,000?
Yes, because if I put that, then that allows me to find the point of intersection using the graph without having to go to the table. There's two different ways we could have done it. We could have gone to the table and looked for when the output is less than 8,000. Or I could have calculated it.
So is it 21 or 22?
Yes. Yeah. Well, it happens after 21 points, whatever that was, 7 something years. So between 21 and 22 years. Between 21 and, well, let me go back to my table. Between 21 and 22 years.
Are we going to have to do an exact value?
No, yeah, you're just answering a question. It happens here after 21 years, right? After 21 years, I go below 8,000. Between 21 and 22 years.
So do you do the same thing for 300?
No, 300, that's your T is 300. So your input is 300. So you'd have to go and change your input to 300. So when your input is 300, what is your output? Well, I could scroll, right, to 300. I don't really want to do that. I could change where I'm starting my table and start my table at 300. And then go back to my table and it'll tell me, right? I have 1.6 people. When input time is 300, there's my population.
Okay.
You got it?
Sort of.
Sort of. It should be under assignments and it should be linear